In some cases, we want to find what regular savings are required to achieve a fund of a certain size. Once again, we can use geometric series to answer such questions. However, it is interesting to note that we can also adapt the amortization formula to provide an alternative solution. Example 2 shows both these methods. When Larry retires in 24 years' time, he wants to have saved a fund of €600,000. He decides to make equal annual savings starting now and finishing 1 year before he retires. The AER throughout is 4%. Part 1. Calculate the value of his equal annual savings. Let A be the value of each of Larry's equal savings. The first saving grows for 24 years, and the last one grows for 1 year. We will write down the equation of value on his retirement date. So by the equation of value, his first saving is A times 1.04 to the power of 24. The 0.04 is the 4% from the question, and to the power of 24 represents 24 years. So the first saving is saved for 24 years, and it grows for 24 years. The second saving grows for 23 years, the next one for 22 years, the next one for 21 years, and so on, down as far as the last saving, which grows for 1 year. And all of these savings, these 24 savings added together, equals €600,000. So we can rearrange this so that the last one is written first and the first one is written last. So we have A times 1.04 to the power 1 plus A times 1.04 to the power 2 plus ... A times 1.04 to the power 24. And that again is equal to 600,000. Now we're going to use our series formula from page 22 of our formula book, which says that Sn is equal to A times 1 minus r to the power of n divided by 1 minus r. So the A is the first term, which is going to be A times 1.04 to the power 1. So that's going to be our first term A. So we end up having A in our numerator, A times 1.04. Technically it's to the power 1, but you don't need to write that in anymore. Bracket 1 minus, or, which is going to be 1.04, because that's what we're multiplying each of these terms by. So the common ratio was 1.04. So A times 1.04 to the power 1 multiplied by 1.04 gives us A times 1.04 squared, and so on. So or the common ratio is 1.04. So we swap both of these ors for 1.04. And then the n is going to be 24, because it's for 24 years the saving grows. So to the power of 24, and that's all over 1 minus 1.04. So we have A times 1.04 times 1 minus 1.04 to the power of 24 divided by 1 minus 1.04, and that's all equal to 600,000. So multiplying this out, we end up with 40.64590829. We have A stuck on, equals 600,000. And solving for A, we're left with €14,761.63. So the value of each of Larry's equal savings is €14,761.63. Or the alternative method. Taking the focal date to be 1 year ago, we can treat Larry's savings as a loan repayment situation, with the first repayment after 1 year, and use the amortization formula. However, we also have to find the present value of his retirement fund. This involves discounting €600,000 for 25 years. So our amortization formula is on page 31 of the formula tables, and it states that A is equal to P times I times 1 plus I to the power t divided by 1 plus I to the power t minus 1. So for the amortization formula, P is going to be the 600,000, which is his saving fund, divided by 1.04 to the power of 25. The 1.04 is going to be 1 plus the 4%, and the 25 is 25 years. So we're discounting 600,000 for 25 years. So that's why we're dividing. So we're going backwards, whereas if we had been going forwards, if we were growing, we would be multiplying. And this is because we're treating it like a loan repayment situation. We're not actually treating it like a fund. So P works out to be €225,070.0814. And our T is going to be 24. Because remember, he's retiring in 24 years' time. So just to be clear on where the 24 came from and where the 25 came from. So the 25 came from the fact that we're treating the focal date to be 1 year ago. So if this is now, minus 1 is 1 year ago. And then he saves for 24 years. So if we go from 24 back to minus 1, we're going back by 25 years. So we're discounting back by 25 years. But in actual fact, he is saving for 24 years. So when we use the amortization formula, we have to use 24, not 25. So we swap the P for 225,070.0814. We swap the 3 I's for 0.04, because remember it's 4%. And we swap the 2 T's for 24, because he's saving for 24 years. And we end up with €14,761.63, which is the same as we got in the last slide. Part 2. If instead he decides to wait 4 years to make his first payment, find the value of each of his 20 equal savings. So if you think this is now, this is in 4 years' time, and this is in 24 years' time. So we're going to let A be the new annual savings, starting in 4 years' time. So this is in 4 years' time from now. Hence, we should treat the focal date as 3 years' time, which is 1 year before he wants to start. So 1 year before 4 is 3 years from now. And to get from 3 to 24, there's a difference of 21. But we're actually discounting backwards from 24 to plus 3, which is now the focal date. So we discount 600,000 for 21 years. Because to go from 24 back to 3, it's a difference of 21. So for the amortization formula, P is going to be 600,000 divided by 1.04, which is the 4%, to the power of 21. And this gives us 263,300.1613. And subbing into the formula now, T is 20. Because if he wants to retire in 24 years, and he's not going to start paying for another 4 years, there's a difference of 20. So we substitute into the formula. So P is 263,300.1613. The 3 I's are going to be 0.04. And the 2 T's are going to be 20. And we end up getting 19,374.09. So if he decides to wait 4 years before making his first payment, then this is the value of his 20 equal savings.